Video 85 Advanced Evaluation Multivariate Analysis Area 9 MCHES Subcompetencies 4.2.1, 4.2.2, 4.2.3. Review the learning objectives for this video. Now we are getting into one of the more advanced evaluation topics, and I think you are really going to appreciate how useful this knowledge is both for the MCHES exam and for your professional practice. As a Master Certified Health Education Specialist, you will be expected to understand not just whether a program worked, but how to isolate the program effect from other factors that might explain the results. This requires moving beyond simple pretest and post-test comparisons into the realm of multivariate statistical methods. The two regression methods you are most likely to encounter on the MCHES exam are linear regression and logistic regression. Let me walk you through the fundamental difference, which comes down to the type of outcome variable you are analyzing. Linear regression is used when your outcome variable is continuous, meaning it can take on any numerical value along a range. Examples include systolic blood pressure measured in millimeters of mercury, body mass index measured as a number, physical activity minutes per week, or a knowledge test score from 0 to 100. When you run a linear regression, the output tells you how much the outcome variable changes for each 1 unit increase in the predictor variable, holding all other variables constant. For example, a coefficient of negative 4.2 for program participation would mean that participants in the health education program had systolic blood pressure readings that were 4.2 millimeters of mercury lower than non-participants after controlling for age, sex, baseline blood pressure. Logistic regression is used when your outcome variable is binary or dichotomous, meaning it has only two categories such as yes or no, success or failure, quit smoking or did not quit smoking, screened or not screened. Logistic regression does not predict a number. Instead, it predicts the probability that the outcome will occur. The output is expressed as an odds ratio rather than a simple coefficient. An odds ratio of 2.3 for program participation in a smoking cessation evaluation would mean that participants in the program had 2.3 times the odds of quitting smoking compared to non-participants. On the MCHES exam, the most common way this distinction is tested is through a scenario that describes an evaluation question and asks which statistical method is most appropriate. Here is a simple decision rule that will serve you well. If the outcome is a number on a continuous scale, choose linear regression. If the outcome is a category such as yes or no, choose logistic regression. This is a high-yield distinction that appears frequently on the advanced examination, and you are going to nail it. Now let us talk about something that is absolutely essential for you to understand as an advanced practitioner, and that is confounding variables. This topic comes up again and again on the MCHES exam, so I really want to make sure you feel solid here. A confounding variable is a third variable that is related to both the independent variable, your program or intervention, and the dependent variable, your outcome of interest. When a confounder is present but unaccounted for, it can distort the apparent relationship between your program and the outcome. The distortion can work in two directions. A confounder can create the illusion of a program effect where none actually exists, or it can mask a real program effect, making an effective program appear ineffective. Let me walk you through a detailed example to make this concrete. Suppose you are evaluating a worksite wellness program that includes physical activity promotion. You compare heart attack rates among employees who participated in the program to those who did not, and you find that participants had significantly fewer heart attacks. Before you conclude that the program was effective, you need to consider confounding. What if program participants were predominantly younger employees in their 20s and 30s, while non-participants were predominantly older employees in their 50s and 60s? Age is strongly related to both the likelihood of joining a voluntary exercise program and the likelihood of having a heart attack. In this case, age is a confounder. The lower heart attack rate among participants might be entirely explained by their younger age, not by the program itself. Now here is the good news. There are 4 major strategies for controlling confounding variables. The first is randomization, which is the gold standard. When you randomly assign individuals to treatment and control groups, confounders are distributed approximately equally across both groups, neutralizing their effect. The second strategy is stratification, where you analyze results separately within subgroups defined by the confounder. For example, you would compare heart attack rates among younger participants to younger non-participants, and separately compare older participants to older non-participants. The third strategy is matching, where you pair each participant with a non-participant who has the same value on the confounding variable. The fourth and most powerful strategy for observational evaluations is statistical adjustment through multivariate regression. When you include confounding variables as covariates in a regression model, the analysis mathematically holds them constant, allowing you to isolate the independent effect of your program. On the MCHES exam, when you see a scenario describing an evaluation result and asking what could explain the findings other than the program itself, the answer is almost always a confounding variable. You should be able to identify the confounder and recommend the appropriate control strategy. You are building really important analytical skills here. Alright, now let us put your regression knowledge to practical use by learning how to interpret the key elements of regression output, even if you are not the one running the statistical software yourself. As an MCHES level practitioner, you need to be able to read and make sense of these results. Let me walk you through the most important components one by one. First, in linear regression, the coefficient for each variable tells you the direction and magnitude of the relationship. A negative coefficient means that as the predictor increases, the outcome decreases. A positive coefficient means both move in the same direction. For example, the coefficient for program participation is negative 5.8 in a model predicting hemoglobin A1C levels. That means program participants had A1C values that were 5.8 units lower than non-participants after adjusting for all other variables in the model. Second, in logistic regression, the key output is the odds ratio. An odds ratio of 1 means no association, meaning the program had no effect on the likelihood of the outcome. An odds ratio greater than 1 means increased likelihood. An odds ratio less than 1 means decreased likelihood. For example, an odds ratio of 0.65 for a tobacco cessation program predicting continued smoking means that program participants had 35% lower odds of continuing to smoke compared to non-participants. Third, you must understand confidence intervals, and this is where a lot of exam questions test your knowledge. A 95% confidence interval tells you the range within which the true population value likely falls. For linear regression, if the confidence interval for a coefficient includes 0, the result is not statistically significant, meaning you cannot rule out that the true effect is 0. For logistic regression, if the confidence interval for an odds ratio includes 1, the result is not statistically significant, meaning you cannot rule out that the odds are equal between groups. Fourth, the p-value provides a probability statement about the result. By convention, A p-value less than 0.05 is considered statistically significant, meaning there is less than a 5% probability that the observed result occurred by chance alone. Now here is a critical distinction that the MCHES exam loves to test, and I want to make sure you catch it. Statistical significance does not automatically equal practical significance. A program might produce a statistically significant reduction of 2 millimeters of mercury in blood pressure across thousands of participants, but that reduction may be too small to have any meaningful clinical or public health impact. The MCHES exam expects you to understand that program decisions should consider both the statistical evidence and the practical importance of the findings. Always ask not just whether the effect is real, but whether the effect is large enough to matter for health outcomes and to justify the program resources invested. You now have a strong foundation in interpreting evaluation data at the advanced level. That is going to serve you really well. Read the scenario stem aloud. Give students 30 seconds to consider options before advancing. The correct answer is B. The correct answer is B. Job type is a classic confounding variable in this scenario because it is related to both the predictor, which is program participation since desk workers were more likely to volunteer, the outcome, which is weight loss since sedentary workers may have different baseline activity levels and weight change patterns. Without adjusting for this confounder, the odds ratio of 1.85 may overestimate or underestimate the true program effect. Option A ignores the confounding issue entirely. Option C is incorrect because the outcome variable here is binary, meaning achieved 5% weight loss, yes or no, making logistic regression the appropriate choice. Option D is incorrect because the confidence interval of 1.12 to 3.06 does not include 1, and the sample may be adequate, but the issue is confounding rather than sample size. Summarize the key takeaways before closing.